So this lesson is going to be on molar enthalpy and calorimetry. So we're not going to be just talking about enthalpy changes. We added this word molar. So what is the enthalpy change per mole of chemical that reacts? Okay. Now we're going to have the same starting point to get to molar enthalpy as we do enthalpy. Calorimetry is the heart of both. Okay. So first I start with a statement that's really important to ultimately getting to the formula we're going to use. Okay. The change in enthalpy, so that is delta H, increases as more limiting reagent is added. Okay. We're going to measure that limiting reagent in moles. Okay. And that hopefully is an obvious statement. Okay. That's a chemical version. If I put more wood in a fire, you're going to get more heat. That's all this statement is saying. I put in more limiting reagent, I get a increased enthalpy change. Okay? So both of those are variables. They change. Every question they change. Even within one question, I might tell you how many moles and what the enthalpy change is. And then I could ask you, what if you tripled the moles? What would the enthalpy change be? And you would just triple it. Okay. However, okay, the ratio of enthalpy change, now I didn't write the word change here, but I mean the ratio of change in enthalpy to moles is a constant, okay? And we're going to learn how to predict these constants and use them, okay? Now enthalpy to moles, that word to implies division. Okay. So now we're building one of the most important formulas we're going to use this unit. The ratio of change in enthalpy to moles. I'm highlighting both of these are variables. Equals molar enthalpy. Now I use a subscript N, delta HM. Okay. Our change in enthalpy is going to be an energy unit. We're going to use kilojoules most of the time. N is moles. And our units of molar enthalpy is just the division of those, kilojoules per mole. Okay. Every chemical for a given reaction type is going to have a constant molar enthalpy. Okay. If you look at methane, that is heating your house or heating your hot water tank, methane releases so many kilojoules for every mole that reacts. Okay? That is never going to change. All you can do is put in more moles of methane or less moles of methane, and you'll get more or less energy. And that can relate to more or less temperature change in your water or the air that's being heated. Okay? So as we work our way through, this is going to be a super important link to get through multi-step questions. That's not going to change. So we're going to calculate molar enthalpy on the next slide. So what steps am I going to take to calculate the molar enthalpy? And we have to do this for the limiting reagent, for the chemical that runs out. Okay. Now you're not going to be asked to do limiting excess reagent calculations like in Chem 20. The question will tell you or imply what runs out. So the first thing we're going to do is the same thing we did before, determine the amount of heat or thermal energy that is transferred into the surroundings, the water. Okay? Heat, which is Q, is mc delta T. Okay? We'll assume we have an isolated environment and whatever that amount of heat is came from our chemicals. Next, same as before, we're going to think of what sign we should have. Okay? We'll put a positive sign if the reaction is endothermic, the surroundings cool down. We'll put a negative if it's exothermic, the surroundings warmed up. Okay, these two pieces are the same as before. They give us delta H, and now we have this new step. We're going to divide that enthalpy change that we just got by the moles of the limiting reagent. Before I go on to an example, I'll just remind you of the two common ways you're going to have to calculate moles. If you have a pure substance, This might look like 10 grams of calcium metal reacts. Okay, well that 10 grams is pure. Okay, you need to take the mass of that substance and divide it by the molar mass, as opposed to a solution where you have a solute and a solvent. You get moles is equal to concentration times volume. Okay, you're not going to see gas calculations like you did in chemistry 20 to solve for moles. So let's solve for molar enthalpy in the following reaction. So again, like the previous question, when you get on a test or your workbook questions, the last line tends to have the question. So we're asked to determine not enthalpy change like we saw before, but molar enthalpy. So that is delta HM. So find the question, make a bit of a plan of how you tackle that question, and then go back and read through the data. So to get molar enthalpy change, we need to find the delta H, and then we got to divide it by the moles of the limiting reagent, and we're told to do this for ethanol. So that must totally run out. Okay. To solve for the enthalpy change in a calorimetry experiment, we need MC delta T, and we need to figure out what the surroundings is. It's often water, but every now and then it's not. So jumping to the middle, the surroundings, ethanol was combusted, but the heat went into, the thermal energy went into 1.63 liters of water. Okay? So the surroundings is water. So I need the mass of water, the C of water, the delta T of water. Okay. So I don't care about this ethanol mass for the MC delta T. That's not where the energy went. I need to just focus there. That is the only mention of the surrounding water. So I have to do a little bit of conversion. We have 3.63 liters, but I want that in milliliters because I know every milliliter of water is a gram. Now your data booklet has the meaning of all the prefixes. Milli is 1/1000th of a liter. Okay, there's 1,000 milliliters in a liter. So this is 3,630 milliliters. Okay. Or because it's water, that's 3,630 grams, because a milliliter is exactly a gram just for water. So that is our mass, 3,630 grams times, this is water, 4.19 joules per gram per degree Celsius, times I need the change in temperature. So what is the difference in temperature? 26.18 minus 19.88. That is a difference of 6.30 degrees Celsius. Okay, my joules and, my grams and grams cancel, degrees Celsius cancel. I'm left with just joules. Now we tend to get really big numbers of joules, and I'll probably convert it to kilojoules. I have 3 measured digits in all these calculations. Okay. But you'd want to keep extra digits till you get to the very end. So my calculator spit out 95,821 joules, which I'm not done, so I'm not going to round that down yet, or 95.821 kilojoules, counting by thousands of joules. Okay. We always have to get joules first. Okay, so that's my first step of 3. Get the thermal energy, the Q, then think of the sign, and please always write your sign in. Even if it's positive, I'd like you to write it in to convey to me you know what sign it is. The final temperature is warmer, So energy was released to make it warmer, so this is a negative change in enthalpy. Okay. Then I just need to get the moles. And the chemical that's all running out is the ethanol. So I need moles of ethanol. Okay. So eth means 2 carbons. Okay. So you should be able to figure out what the formula is of ethanol and get the molar mass. Moles of this pure substance is mass over molar mass. This isn't a solution. The ethanol is a pure 3.5 grams divided by the molar mass of ethanol, which is 46.08 grams of ethanol per mole. Grams and grams cancel. We're left with moles on the top, and you get 0.0760 moles. So much less than a mole, less than 1/10 of a mole released that 95 kilojoules. Again, you would want to keep all the digits in your calculator for both the red number and the green number. And then at the very end, I'm going to round to 3 sig figs because that was the limiting significant figures in both pieces of data. So I'm after that division. Write that minus down first. I see students forgetting to put the minus in their answer sometimes. 1,200, and I'm going to round it to 60 kilojoules per mole. My 1, 2, 3 sig figs. That 0 is just a placeholder. Okay. And that's our molar enthalpy. Okay. This is a value we could look up in a data table and compare. Okay. Because ethanol, the combustion of ethanol should always have the exact same molar enthalpy. Okay. This is a constant. Okay. The 2 values we just used to solve, these are variables, but the ratio is always the same. Okay. So that's how you calculate molar enthalpy from calorimetry data.